So welcome back to Lean Together 2025. Our next speaker is Jakob von Raumer, who's going to tell us about building a verification framework for smart contracts.
Yes, yes. Fancy title slide because this is an industry talk. So yeah, thanks for the introduction and thanks for the opportunity of speaking here. I guess this is one of the few formal verification talks in this year's Lean Together, and a bit of a change of topic among all the math formalization talks. So this is a project that's been like on the slow burner for me for the past 2 years now. And I kind of wanted to report on basically on the process of developing a framework for formal verification. Basically showing how thin of a layer of metaprogramming you actually need in order to get going to verify some proper computer code. And the setting I'm doing this in is for my employer, who's called Lindy Labs. So we're building what's called decentralized finance protocols, so smart contracts that run across different computers. So you probably all know that this usually runs on a blockchain. And so the language I'm dealing with is called Cairo, and the system I'm dealing with is called Starknet. And Starknet is a zero knowledge scheme that is used to outsource computation from a blockchain. And the blockchain in question is the Ethereum blockchain. And it's very expensive to run the code of smart contracts directly on this blockchain because it has to be run by everyone who's verifying the validity of the blockchain. So the execution of the code of this smart contract has to be repeated over and over again on various computers. So if in the end you want to scale up your product and you want to run a code that basically iterates over like a long list of customers or so, then it becomes mandatory to not run the code on the blockchain itself, but to outsource it. And these so-called layer twos are one way of outsourcing this by some sort of trusted computation mechanism. But I don't want to get into the cryptography that's behind all of this. The important thing is just that it's a very quirky language with a very specific target in mind. And also, like on this slide, there's the term prover and the term verifier. This is not the lean prover and the verifier or the elaborator of lean, but this is the prover and the verifier of the zero knowledge scheme that the user programs that we want to verify are using. So why is Lindy Labs interested in verifying this? There's lots of different smart contracts. Some of them are lending pools, some of them are market makers. So these are contracts that move large amounts of money. So whenever something goes wrong, something usually goes really wrong. And maybe somebody just carries out millions worth of money, or somebody just some money just gets burned. I mean, this is not necessarily a zero-sum game. Sometimes you just lose money because somebody put the wrong address in the configuration of a smart contract. Yeah, there's lots of documentation of these things happening over and over again in all of this crypto world. And so we try to bring a bit of sanity in there by trying to make sure that this doesn't happen. And of course, our method would be to formally verify smart contracts. So what's Cairo? It's a language that's in its current iteration, Cairo 2, has a syntax that's pretty much inspired by Rust, and also some mechanisms that are pretty much inspired by Rust, for example, like the ownership model. And this is pretty nice because lots of the programmers in the crypto world, they kind of know Rust because it's always been like a favorite language of the whole ecosystem. For example, interfaces between contracts are just realized by trades. It's just the syntax of Cairo is just geared to be very well suited for the kind of developer that would appear and would use it. One quirky thing about it is that while there's integer data types, unsigned and signed integer data types, the most primitive data type that's the underlying basis for everything else is just something that's called feld 252, which is just short for a member of the prime field, z modulo 2 to the power of 251 plus 17 times 2 to the power of 192 plus 1, which is just a big prime. And the reason for that is also because the cryptography just works that way. We're just programming in a high-level language, but in the end, basically all of this is compiled down to a sequence of polynomials. And the execution of a program then consists of finding common roots for this sequence of polynomials. And then these roots are basically handed over to the blockchain as a proof that you've actually executed the code with a certain set of results. And before the current iteration of Cairo, people were using what's now called CASM, like for Cairo assembly. Starknet, who was developing Cairo, usually used to advertise that as the language that people should use, but it felt very awkward because you had to explicitly have program counters and frame pointers, so it was just a very low-level language. And in the end, because we're not dealing with programs that run on a real machine, memory is only once, so we can't use the same memory cell once. So there's lots of infrastructure around to be able to cope with that fact, and it didn't have a typing system. And adding to that, there was a different problem. Like on the first slide, you saw that there's a role in the whole system that's called sequencers, and these are the people who actually run. Who actually compile the different executions into so-called blocks and then run them. And they're paid for doing that. And one really big problem was that the sequencers also had to pay the cost for failing transactions, and then had the opportunity to, because you couldn't force them to do that, they had the opportunity to perform kind of censorship by being able to choose which executions they would execute and which they would leave out. So what was needed was an intermediate representation, and that's now called Sierra, which is just some weird backronym made up from safe intermediate representation, which acts as an intermediate between the Cairo assembly code and the high-level Cairo code. And that's a total language. That's because we don't want any failing executions, and it's linearly typed, and that's not enforced by the language itself. But the Sierra programs that we're dealing with are all already in single static assignment form, which means that no variable is overridden. And loops are already converted to recursive function calls. And what makes this language not only suitable for this whole zero-knowledge scheme, but also for formal verification, is that every code in this function, in this language, boils down to calls to a set of roughly 250 what's called libfunctions, like library functions. And library functions can be anything from calling other user-defined functions, performing type conversions, stuff that's very specific to Starknet, for example, gaining access to the execution information, to persistent memory storage, and also drop and duplicate functions for some types for which the linear typing doesn't hold. So to give you an example of what Sierra looks like, it's a super simple syntax, and every Sierra file always consists of 4 sections. First, we have a section which is just consisting of type declarations. So these are just basically short forms for the types we are using, and would also declare names for any enums and structs and any more complex types that we're using. And then in the second part, we're declaring all of the library functions that we're using, and we're already specializing them. So Cairo itself has polymorphic functions, and Sierra doesn't have polymorphism, so we need to monomorphize them in Sierra in this section. And then the actual code, the actual statements of the functions that we're declaring are in the section 3. So this would be like a call to something like a duplicate function that takes the thing that's in the 0 memory cell and copies it to the second memory cell, and then we can multiply both of these instances and put them in the first memory cell, and then we can store that and then return it. And so that's what this looks like. We can also have branching there, but in the end, it's just a list of calls to the libfuncs that we've declared in the second section of the Sierra file. And the fourth section then defines the exported function, so the signatures of the functions that we're defining. And the at 0 basically means that the definition of the function that's called double starts at the first line of section 3. So yeah, that's what Sierra looks like. And because it's all just a set of calls to these libfuncs, having a pretty accessible semantics is very easy for this language. Obviously, we have to interpret all the types in Sierra as corresponding lean types. For example, we just interpret the enums in the language as sums and the structs as products in lean. And then for each of the libfuncs, we just define a fixed semantics. And there's work by Jeremy Avigat, who's basically verifying that these libfuncs on their implementation all do what they should do with respect to the compiler that converts Sierra code to Cairo assembly code. And then we just iterate over the program code, and basically we just compile one big mathematical expression. And for example, if we have this doubling function, which just takes a felt like a field element and doubles it, it would just start at the first line and plug in the semantics for the duplication libfunc, and then we'll plug in the semantics for the multiplication libfunc, and then something like the thing you see on the right here would pop out of the of this translation. And then the idea is that obviously this is not in a nice form. So this has this completely useless existential quantifier over these intermediate variables. And the idea is then that the user who wants to verify Cairo code then provides their own specification, which is currently manually written, but obviously we can also imagine this to be, I don't know, written by an AI in the future, and then proves that the manually written specification actually is implied by the automatically derived specification. And so that's the idea of the framework. And the framework, which is called Aegis, would be used in the following. So we have like a user command that just loads a Sierra file, just saying Aegis load file. And then we have a different user command that just Aegis spec for a certain function that's exported in that Sierra file. And then we can just give a nice looking specification of that function. And then it's the user's task to actually prove that this specification is correct. yeah, I mean, I don't have a info view on this slide. So this wouldn't be like a very sophisticated proof. In lots of cases, actually, ESOP can prove these things. Whenever the specification trivially matches the automatically derived specification, then actually ESOP can most of the time do it. Because as we've seen, the automatically derived specifications usually consist of lots of conjunction and disjunctions and existential quantifiers. And so ESOP just goes ahead and just disassembles these, and for the disjunctions just applies case distinctions. And then we have another command that's called Aegis complete, which is basically just acting as some sort of check whether all of the functions that are exported in the Sierra file are actually specified and proven. So this would tell you, oh, you've forgotten to prove the specification of this and this and this functions. Oops. So yeah, on to how I implemented this. And I guess the message I want to bring across is that Lean provides you with exactly the tools that you need to build these kinds of frameworks. Like parsing the Sierra files, not in the end, also because Sierra is a very simple language, just took me 200 lines of code, which includes the AST definition and the parsing and the elaboration. So I'm just like showing a few examples here. For example, you can see that the data type of Sierra files just consists of the 4 sections that we've seen earlier in the example. And we're also lucky that in many cases we can just reuse Lean's own parsers. For example, the identifiers that we use in the statements just happen to be compatible with Lean's own identifier parser. Then for the type system, most of it is pretty straightforward. So we for the primitive data type f, we just use zmod, and in the past few weeks we moved from using zmod for the unsigned integers to using the bitvec data type that's now in the core. And then we have a quote function that just converts the codes for the Sierra types into the actual expressions. And you see that we're using the QQ package a lot in order to give some static guarantees that whatever we write down as a translation also makes sense, instead of just building up expressions with a blindfold. Some of the more difficult stuff is that Cairo has recursive types, so you can implement something like the natural numbers in Cairo, but you were lucky that they always, all of these types want to have a fixed width, so that's why they're only allowed recursive calls in what's called boxes, and we just implement the semantics of these boxes to be just a heap that can be accessed. And so we just translate all these boxes, which behave like the box type in Rust. We just implement them as nat. And then for actually implementing the semantics, we just traverse the statement, and we have a little data structure that's sort of a list tree that's representing the disjunctions and the conjunctions that we want to get out in the end. Yeah, then we just compile this tree into a single expr. Yeah, there's there's some intricacies, but again, like the simpler your language is, the more straightforward it is to actually do the meta programming for this kind of stuff. And then the last bit that's missing was writing the actual user commands. So that's also been like roughly only 200 lines of code. We've just defined user environment extensions that hold all the specifications and all the proofs. And the only thing that's a bit difficult is that by design, Sierra is monolithic, so you don't have imports in Sierra. You compile your program, and even if it uses libraries, it will just generate one huge Sierra file. So in our cases, some of the Sierra files were like 5 megabytes big, just the text file. Yeah, so having a modular verification framework for this monolithic file design was a bit difficult, and so we're still not completely sure how to actually reconcile specifications that were given in an import of another lean file. So we want to be able to specify and prove in different lean files or in different lean packages, and then use the specification by just importing the lean file. And that turned out not to be too easy. One of the first things we did after building this prototype of a framework was verifying the standard library of Cairo, and lots of the functions there are super straightforward. And oftentimes, giving the specification was the harder bit, and proving it was the easier bit. The only thing is that sometimes we have to help Aesop a little bit by helping to deconstruct like the chain of existentials and of conjunctions. But I think also with what's on our mind for the next months is to actually write a custom Aesop configuration that might be better suited for that. And you see that, for example, we have this specification and this proof of the expect function of an option trait, which just does the same as the option trait in Rust. So it's just like an option type. And one thing we haven't found out is how to properly do that in a polymorphic way. So as I said, Cairo itself is polymorphic, Sierra is not. And so we get the already monomorphized definitions in Sierra, but we want to be able to write a polymorphic specification for those. And that's also something that we've not solved yet. Yeah, some more examples. For example, like this is just Starknet standard function to get the caller address. The S and the S prime are the system state of Starknet. And so the S equals S prime just means that the system state doesn't change by calling this function. And then you see something like the power function. This calculates 10 to the power of n in a recursive way by basically halving the exponent and doing a recursive call. And because we're not allowed non-terminating executions in Cairo, we have something called gas, and we have a way to allow for specifications to contain references to the use gas. And so this specification basically says, okay, if the exponent is less than 39, because that's the biggest that fits into this data type, and the base, the exponent plus 1 times the cost of one call to the power function is less than the gas that we are available, then row equals dot in left. So that means that we're using sum types for all of the enums. So that means that the execution succeeds with the expected outcome, and the row dot is right just means that it fails. And so some even more advanced example. So this is not really nice to look at, but this is like the first attempt at actually verifying our own financial product, which is a controller that controls the interest rate of a certain contract. And so above you see the formula that it tries to implement, but obviously there's a numerical error to all of this. And basically what we did is that we've put in some preconditions and say, okay, if all our input values are in a reasonable range, then we can contain the numerical error to a reasonable range, even though this is highly nonlinear and contains fractions and so on and so forth. So yeah, but this was a bit of work to verify, but I guess we're probably the only company in the space that kind of has managed to do a verification of this kind of algorithm. And as you see below, I'm using the reference to the real numbers quite a lot. So we actually compare this implementation against an idealized version of the same controller. So we can actually compare the numerical error with regards to if we had infinite precision. Yeah, as I said, more automation. We want to have polymorphic specification. And we've not completed this verification for the Cairo standard library, and we've also not tackled the verification of some of the other libraries that are very commonly used in the crypto space. And then I also, I forgot the last bit of the last bullet point. I also want to separate the Cairo-specific parts of the whole framework from the non-Cairo-specific parts, so that maybe we can reuse the whole thing for other code as well. Maybe even like non-crypto code, just arbitrary intermediate representation that are also in the single static assignment form. Okay, thank you for listening. I'm happy to take questions.
Thank you very much.